joint work with Elise Gourier from ESSEC Business School and Hugues Langlois from Barclays Corporate Investment Bank. As you can see, the title of this paper is Equity Risk Premium with Intertemporal Hedging. So the big question that we ask in this paper is, what is the contribution of intertemporal hedging in the total equity risk premium? When you think about it, think about an investor trying to figure out, a representative investor trying to figure out like the average excess return, a 1 month average excess return or a 3 month average excess return in a multi-period economy. And we know that the expected excess return is an important input for portfolio allocation. If you think about the simple mean variance allocation, where we all know that the optimal allocation is the excess return divided by the risk aversion times the variance, like you can see clearly that the expected excess return on the market is important. If you also think about the KPM and also the Pharma French factor and extension of the Pharma French factor, the expected excess market return is an important input as well component. And we know also that if you use historical data, expected excess return is hard to estimate. Usually people make assumptions, researchers make assumptions about the data generating process. We also are aware that the stochastic discount factor, as asset pricing researchers, that the stochastic discount factor is related to the probability, the physical probability, and the risk neutral probability, because it is a ratio of these two, risk neutral to the physical, right? And if you know the stochastic discount factor, you know the risk neutral probability, you can infer the physical probability. It turns out that when you use the traditional approach, which is using historical data, or use the traditional predictors, you confront them using the Gourier and Welch auto-sample R-squared. And you look at the recent paper by Gourier and other co-authors, they show that many predictors actually fail to deliver a robust auto-sample prediction. Now, so there's a recent literature over the last few years that is trying to use option prices to measure the equity risk premium from the data. So the cool thing about this approach is that it does not rely on historical data, but again, we do not live in a perfect world, right? We need to make a mild assumption about stochastic discount factor. So if you take all those things into consideration, you can derive under non-arbitrage conditions, you can derive a bound on the equity risk premium. So the question, whenever you derive a bound and equity risk premium, the question that you ask yourself, how important is this measure? Okay, you want to know if this measure contains like a rich set of information that allows you to precisely measure the expected excess return. So in this regard, you can run some auto-sample tests and to clearly see what is going on, and also use the measure that is proposed by Kerry Bach in his JFE paper to test the tightness of the bound. As I said before, if you know the risk neutral measure and you have mild assumption about the stochastic discount factor, you can recover physical moment. Everybody knows here that, and also in the literature, that the paper from Briden and Lichtenberger like allows us to recover the risk neutral distribution. And also the technology that was provided by Karen Madan and also Bakshi, Kapadian and Madan and other researchers, where you use the spanning formula, allows us to also recover the risk neutral quantities from option prices. So the nice thing about this approach is that it allows us to recover the equity risk premium at each point in time without using historical data. Now, let me get quickly into the motivation and talk about our contribution. So before I start with our contribution, our motive contribution, let me remind the audience about the Ian Martin bound, which is what you see here. The expected excess return on the market is bounded by the risk neutral variance discounted by the return on the safe asset. And this bound is consistent with the log utility, with the log investor. And in a paper that I wrote with Laudis in JFE, we show that the expected excess return can be bounded by a function that depends on all moments of the distribution. So what is the difference between Ian Martin and the paper with Laudis is that Ian Martin focused assume that investors have long utility. The paper with Chabi-Yo and Laudis makes no assumption about the functional form of the utility. So then derive a bound. It turns out that this bound is actually robust and it predicts well the expected excess return compared to the benchmark of Ian Martin. But when you look at these two papers, they both they focus only on a single period economy. From T today, this is shown here, today to tomorrow, which is T1. So there's no rebalancing between today and tomorrow. Tomorrow is the end. So in this paper, what we did is that we have a representative investor maximizing the expected utility, and the terminal date, which is the investment horizon, is TN, and today is lowercase t, and the forecast horizon is T1. And between T1 and TN, you have, different time periods. So what we are really interested in is to find the expected excess return over the same time period as in the previous papers, but assuming that the investors horizon is TN. So investors actually make decisions in a multi-period economy. They are able to rebalance their portfolio at each time, like at T1, at T2. So this is not actually, has not been actually used so far in the literature. And we are actually showing this paper that taking into account intertemporal hedging, the risk of shift, intertemporal shift, like in economic environment is really important to measure the expected excess return and other risk physical quantities. So it turns out that the bounds that we were able to derive, as you could see here, which is on the right-hand side of this inequality, is a function not only on the market return at T1, it depends also on the residual moment of the market return at a higher, the investment horizon, which is TN. So what you really need to be able to implement this bound, this bound is not a set of options with just one maturity, but you need options with multiple maturities. So you need to exploit the information set in the cross-sectional dimension, right? Cross-sectional dimension of maturities and moneyness as well. So this allows us to get a precise estimate of the expected excess return. So in this paper, we also provide additional results on the physical variance and the crash probability physical measures. So in terms of finding, so we found that the intertemporal hedging actually leads to a higher equity risk premium, especially during market calm, and it leads to a still higher equity risk premium during crisis period. But the contribution of the intertemporal hedging during normal times is very high, up to 80%, versus the contribution of intertemporal hedging during bad times, which is about 30%. By bad times, I mean recession period, or maybe let's say stress time periods. We also document that when the probability of crash is very high, here we are assuming like 10%, we can, maybe you have your own number, but here we're assuming that, a threshold of 10%, if it is very high, investors actually tend to be like a short-term investors. So during crisis period, investors shrink the investment the investment horizon. And this is kind of consistent with many papers, Schleifer's paper in 1993 and co-authors. So where they actually predict that investors' time horizon shorten during a period of uncertainty due to increase in the risk aversion and limited attention. So we are kind of providing a nice framework, a nice empirical result that, clearly show the fact. Now, we also found that during normal times, investors actually behave more like long-term investors. And this is actually also consistent with some papers by Campbell in 2004 and co-authors also. They also found that investors actually shrink their investment horizon during bad time and actually become like long-term investors during like normal times. When you think about our equity risk premium, as I said before, one way to test the performance of our equity risk premium is to look at the out of sample R squared. And when we look at the out of sample R squared compared to the benchmark, here I'm assuming that Chabi-Yo and Laudy is the benchmark because when you look at the literature, it turns out that several papers have shown that even if you look at Kerry Back's paper, Chabi-Yo and Laudy's measure actually outperforms Ian Martin. As a result, we are not really comparing our measure here to Ian Martin directly. We are comparing our measure, the performance of our measure to Chabi-Yo and Laudy's. And it turns out that the outperformance that we get in this in our analysis is the largest for short horizons and during normal time periods. Now, let me walk you through the theory. So you will see a little bit of a few mathematical formulas, but just relax, and I won't show too many, too many formulas. So because it is really important for you to understand how we arrive at this measure. So let me start with the following. What you see here is an equation. You have a representative investor that maximizes the expected utility. And omega t is the allocation today. Omega T1 is the allocation at time T1. And the U is the utility. E is the expectation under the physical measure. And W from T to Tn is the terminal wealth. You could see here the terminal wealth is a function of the previous wealth times the realized returns. And you could also see that the lowercase letters here are excess returns. This is showing this is showing up below here in the last two equations here. Okay. Now, in this audience, you might ask the following question: why we are not really including consumption here, right? So we did derive some results including consumption in the appendix. But it turns out that even with consumption, our results remain in lower bounds, assuming that the correlation between consumption and the market return aligns with the correlation between market and consumption in the data. So that's why we did not put that, because with the result with consumption, actually, it's a little bit messy. You have too many formulas. We left that in the appendix. So this does not really change our bounds here. Now, the SDF that you recover from this framework is in blue here. Basically, in blue, what you see is the inverse SDF, which is V divided by its expectation under the risk neutral measure. And V, think about V, which is a random variable, as the expectation under the risk neutral measure at T1 of the inverse marginal utility. So what you see in the parentheses here is a ratio of two terms. The numerator is just a constant because it depends on the risk-free rate here, return. And the denominator actually depends on two terms, the market return from today to tomorrow, and the market return from tomorrow to the investment horizon, which is Tn. So what we will do in this paper is that because the functional form of the utility is not known, we use Taylor expansion series around the market return equals to the risk-free rate. It could be a bivariate Taylor expansion series. So this will allow us to get away, from specifying the functional form of the utility. At the same time, we need to provide some preference parameters values. So I'll get into that later on. Now, how did we get our formula of the expected excess return and crash probabilities in this paper? So this is a identity, which actually looks more like is familiar with the same formula that you get under the physical measure, where you have the negative of the covariance, which is equal to the risk premium. But when you think about the risk neutral measure, you have an equivalent expression, but instead of using the SDF, you use the inverse SDF. And the negative sign disappear in front of the covariance, because here we are using the covariance under the risk neutral measure. And the physical probability also is given below. That's the last equation that you see on this slide. So all we need to do here is to replace our stochastic discount factor, our inverse SDF, in this covariance term, and also in the physical probability, the right-hand side, and then expand. So this allows us to have nice result. So now, before I present the result, I mentioned earlier that we use Taylor expansion series to kind of expand the inverse marginal utility using a bivariate Taylor expansion series. So this, we are left with investors' preferences. So we in terms of functional forms, there's no need to specify the functional form anymore. We got away with that, assuming that regularity conditions are satisfied. So now the two preference parameters that are really important in our framework are the risk tolerance, which is tau, and think about tau as 1 over tau as the risk aversion, basically. And you have the skewness preference parameter, which is rho t here, is basically related to the prudence adjusted by the risk aversion. So the risk aversion is pretty standard. The skewness preference parameter is because it is a function of the prudence, and risk aversion is not new. And as you could see here, if you look at the literature, the risk aversion is often bounded, like you have a lower bound on the risk aversion of 1. And if you look at the literature, many papers, several papers, you also see that the skewness preference parameter is bounded by 2. Now, our SDF, inverse SDF, it has the following form. It looks like it's equal to this ratio, which is 1 plus Z1 divided by its expectation under the risk neutral measure. So what is really nice here is that you could see that Z is a linear function of the excess return here, and also a linear function of the squared one, right? And the contribution of our framework, the second order expansion here series, is that we are able, by doing so, to add a third term here. So what it is actually showing is that there's no need to make time series assumption to show that the stochastic discount factor depends on volatility. No, all you need is a multi-period, economy, and use some Taylor expansion series. You see clearly that the stochastic discount factor depends on the market, excess square market, and the future volatility under the risk neutral measure. And the coefficients A1 and A2 are in the last equation. As you can see, A1 is basically the risk aversion, and A2 reflects the skewness preference parameter adjusted by the risk aversion. Now, this is our first result. So as you could see, the equity risk premium is bounded. So it's bounded, as you could see, by this term that you have here. Okay, and what you can see here is that you have blue expressions here, the expressions in blue here, and the expression in blue, these expressions are new terms, and they show that it turns out that these terms are important empirically. And the numerator, in the numerator, the blue that you have is the leverage effect, which is known in the literature, usually I think under the physical measure, but here it turns out that this one is under the risk neutral measure, is the correlation between the market and the future volatility. You also have the moment as well here. So our bounds depends not only on the risk neutral moment of the distribution, but it also depends on the leverage effect and also the expected future moment as well. To be able to measure these bounds, you need not only to have options at maturity T1, but options at maturity Tn as well. You need multiple options with multiple maturities. So now let me move to the second result about crash probability. So as you could see here, the crash probability that we have is a ratio of 2 terms. So think about, here you have so many expressions, but think about these expressions are truncated moments, because the crash probability, what it does is that it kind of put a certain weight on the extremes, okay? And what it turns out what we have here, it turns out that the additional terms that you see in blue here, the contribution of our framework here when measuring the crash probability, this is due to the intertemporal hedging rebalancing, being able to rebalance your portfolio at each point in time. Okay, so I'll come back later on how to measure these quantities from option prices. Okay. Now, before I get into that, it is important for me to relate our measure to Ian Martin measure and also to Chabi-Yo and Laudis, and also to well-known utility functions. So you just need to assume that A1 is equal to 1 and A2 to 0 to get Ian Martin. To get Chabi-Yo and Laudis, you just reduce your model to a static economy. So the blue terms actually that you have here, blue terms disappear. And to get a measure in a framework where you have investors with a CRRA utility, you set the coefficients A1 and A2 as follow. And if you want to get a measure where investors have a CARA utility, then you set A1 and A2 differently. So roughly our measure is general, and what we'll show later on is that it helps predict excess return, and it also helps highlight new facts that we see in the data. Now, to be able to measure these quantities, the risk neutral expressions can be measured using Carr and Madden. These are the first risk neutral measures that you see. This is the risk neutral moment of the simple return. The next one is the risk neutral moment of truncated returns. Now, in the second bullet point, what you see is a different risk neutral moment that starts from T1 at T1. The risk neutral moment, which is measured at T1. And the next quantity, M star T V here on the script here. So this term actually is an expectation of a future risk neutral moment. It is difficult to use Carr and Madden. You cannot just use Carr and Madden to measure these quantities. What we did is that we need to make mild assumptions. By mild assumption, I mean assuming that this under the risk neutral measure, this one is close to the excess return squared plus an error term. And then using this specification allows us to recover data from option prices without using any time series data. Now, in terms of empirical results, so the data is standard, so I won't get into that. We use the S&P 500 index. We use the volatility surface, and the data is from 1996 to 2023. So what you see here is these are the results when the risk tolerance is set to 1, which is more like setting the risk aversion to 1, and the skewness preference parameter rho, which is equal to 2. So the top graph actually shows 2 time series. You have the blue one and the red one. The blue is the equity risk premium when you actually ignore the intertemporal hedging component, right? So, and this is a 1 month equity risk premium. This is an annualized 1 month equity risk premium. But the red time series, it's the equity risk premium over the same time period, but assuming that investors has a long horizon. By long horizon, I mean like a 1 year horizon. Have a one year investor, right? 1 year horizon, but the investor is interested to learn about the expected excess return over 1 month, although the investment horizon is 1 year. What you see here is that intertemporal hedging leads to a very high equity risk premium. Okay, always higher than the time series in blue. And to check this even more, we look at panel B and computed the contribution of the intertemporal hedging in the total equity risk premium. So the blue time series in panel B, it shows the contribution of the intertemporal hedging when the investment horizon is 1 year. Although we are focusing on like a 1 month equity risk premium. So here it is important for me to mention that we have a forecast horizon, which is 1 month, and the investment horizon, which is 1 year, right? So when you use a forecast horizon, which is 1 month, and investment horizon, which is 1 year, so the contribution of the intertemporal hedging is up to 60%. That's it. You can see the time series in blue. Now, when you increase the investment horizon from 1 year to 2 years, it appears that the contribution of intertemporal hedging in the total equity risk premium is up to 80%. It's pretty high. This actually shows that intertemporal hedging cannot be ignored when we try to measure the expected excess return on the market. And it appears that the contribution of the intertemporal hedging is the highest during normal times and the lowest during crisis period. During crisis period, it's still important, but it's not as that important compared to normal times. On the next slide, what we did is that we asked ourselves, how can we use our measure to predict, excess return, and how can we compare it to the benchmark? So what we did here is that you can see in this table, you have panel A. For me, panel A is the result when we use the auto sample, we got the auto sample R squared. And panel B are the result by focusing on the certainty equivalent. Focusing on panel A, so if you look at the first column, it actually shows the investment, the forecast horizon, which is, we are interested in the forecast for forecasting the excess return over this period, like 10 days, for example, or 1 month or 2 months, if you look at the first column, to 18 months. Now, if you look at it on top of panel A, you have 1 to 24. These actually represent, these numbers are investment horizons. So from 1 to 24 months. Again, our theory works for any years. It works for 20, 30 years, whatever. But we are kind of limited because we are using options. In terms of maturities, we have the highest available that is liquid when you think about the market is 24 months. Now, when you look at the second column here, it shows the auto sample performance for Ian Martin measure. You look at the third column, it shows the auto sample performance for Chabi-Yo and Langlois. Now, what you have in this matrix, upper triangular part here, are the auto sample R squared when we use our approach. Let me focus, because I have so many forecast horizons here. Let me focus on, for example, I choose 3 months. Okay, if I choose 3 months, Ian Martin result theory deliver like a 1.34% out of sample R squared. Our measure delivers like a the paper with Chabi-Yo and Langlois actually delivers a 2.03%. But our current framework, when we vary the investment horizons from 4 to 24 months. You could see clearly that the auto sample R squared increases and then it doubles, like it's almost like 4.47% at 24 months. When you choose an investment horizon, a forecast horizon of 6 months, you have in Ian Martin paper, you have 284. And in my paper with John Langlois, we have like 456%. These are in percentages. And it turns out that in our current framework, the auto sample R squared for the same forecast horizon, it reaches its maximum at 24 months investment horizon, 8.14 compared to 456% in Chabi-Yo and Langlois. This is a significant boost. Now, if you focus on 12 months, you can see 1.05, Ian Martin 385, 87 in our framework with my framework with John Langlois. In this paper, you have about 6.23%, right? Now you can go up to 18 months where you have a negative value with the Ian Martin case and 143% in Chabi-Yo and Langlois, and here you see have 274. But overall, like you could see here that it seems that when we increase the investment horizon, the auto sample R squared increases, it reaches a threshold. When you pass this threshold, it actually goes down. It seems that there's an optimal investment horizon here. And the last column actually shows the performance by using an average value of all measures across the investment horizon. So basically, if you use like a 1 month, for example, you cannot vary like the investment horizon from 2 months because the investment horizon need to be higher than the forecast horizon. That's why you see the blank space here. So using that, we average all these values, average returns using all these investment horizons, and then you try to predict the excess return, and you get this 165. So the last column is not the average of the out-of-sample R squared, but it's just the performance of the average of the equity risk premium across all these investment horizons. Okay. So it seems that there is an optimal investment horizon that is higher than the forecast horizon. Now, again, to briefly summarize this, we have like a significant outperformance between 3 and 9 months. Okay, between 3 and 9 months investment horizon. Now, when you think about the certainty equivalent, you have the same format pretty much here. What you see is that you have the certainty equivalent that increases. It reaches a maximum between 9 months. This column is 9 months. If you look at numbers here in this area, they are significantly higher than other numbers. Now, you might ask, what are the stars here? The stars that we have in the table. The stars actually clearly show that our out-of-sample R-square are significantly higher than the benchmark, and the benchmark here is Chabi-Yo and Laudis. So this actually clearly shows that taking into account intertemporal hedging is important. And it appears that if you just increase the investment horizon, you reach a threshold. But the question is that, how do we figure out if the threshold is time dependent or not? There's an optimal threshold for sure that gives you the highest out-of-sample R squared. So how do we figure out if this threshold is time dependent? To be able to answer this question, we kind of maximize the out-of-sample R squared over a window of 90 days past observations. And this allows us to find the optimal one. And it appears that the optimal threshold is a threshold that gives us the out-of-sample, the highest one, is time dependent. I'm going to show that shortly. Now, this table actually shows the out-of-sample R squared in the last column of this table when we use the optimal investment horizon. So we have add numbers in other columns to be able to compare to the previous result. So the second column is the unmatency, the second one is Chabi-Yo, the third one is Chabi-Yo and Laudis, and the remaining columns from the fourth one, fifth one, and fourth and fifth are the out-of-sample R squared when the investment horizon is either 1 year or 2 years, okay? And you can clearly see that up to a forecast horizon from, up to 4 months, right? 4 months, if you compare these numbers in the last column from 384%, to 547% to the previous columns, these numbers are significantly higher. And then you can see that we get the best result when we optimize that. But when you go beyond 4 months forecast horizon, the optimal investment horizon is equal to 2 years. That's what we are getting out of this table. So this is kind of interesting. So we also look at the certainty equivalent. So we have some similar measures. But think about the certainty equivalent as, is a function of the equity risk premium and the variance. So over there, you need to be able to predict well these two terms, explain well these two terms to be able to get a better measure of certainty equivalent. Now, let me turn into the investors' horizon. So here, what we notice is that there's an optimal investment horizon. And then based on our previous analysis, we notice that in quiet time, investors' horizon is long. And then in bad time, investors' horizon is short, right? So what we did is that because in the previous table, we are able to maximize this up to 4 months, we just set, the forecast horizon to 4 months. We could have set this to a different horizon. So when we set the forecast horizon to 4 months, in panel A here, we plot the equity risk premium, which is not new. We know that. We did that that's what we get in the paper. But what is really interesting is that we wanted to see the implied investors' horizon. That's what we did plot here in panel B. So by maximizing the out-of-sample R squared, using the past 90 days, what you see is that the investor horizon, actually investment horizon actually changes. It switches from normal time periods, to bad times, right? During normal time periods, you can see that it's almost 24 months all the time. It reaches the top here, which is the the y-axis is in days. Okay, so that's why you have like 700 here. So roughly this is more like 24 months. So it's always high when the market is calm during normal times. But during bad times, during crisis period, you can see that the optimal investment horizon is actually close to 5 months. That's the lowest. Okay. Now, to reconcile to this finding with the crash probability, kind of that actually reflects the fact that the market is in crisis. What we did is that we plot the crash probability for using two other benchmark, Chabi and Laudis, Ian Martin. And the top graph here shows clearly the time variation in the crash probability. So as you could see here, the crash probability varies over time. And the blue one is the crash probability in our framework. So the yellow one, I believe it's just yellow, is a crash probability in Ian Martin. And the red one is a crash probability when you use the Chabi and Laudis framework. It appears that over time, the crash probability in our framework is always lower than the crash probability in other benchmark, right? Benchmark framework, like when you use Ian Martin or Chabi and Laudis, right? But it's always lower than these benchmarks, but only during normal times. But during bad times, they tend to be exactly identical, close to each other. So this can be seen when you look at the graph below it, which is the green one here, right? The green one clearly shows you that what you see here, when you see that is close to zero, it's when all these measures of crash probabilities are identical. So this is when the market is experiencing some stress. And also during crash period, for example, you have 2008 crisis here 2001, 2002. And as you could see here, you have significant difference. The contribution of this is basically due to the intertemporal hedging. So the contribution of the intertemporal hedging also, when measuring the crash probability, turns out to be very important during normal times. But during bad times, intertemporal hedging plays almost no role in measuring the crash probabilities, right? Now, what we did next is that to be able to understand better this, because we found that investors switch the investment horizons from, when the market experienced like a stress versus normal times. What we did here is that we plot a 10% crash probability over time. And then at the same time in the panel B, which is below it, we plot also the investors horizon, investors optimal or like investment horizon. What you could see here is our goal is to check how the crash probability moves along with the optimal investors implied horizon, right? Investors implied horizon. You could see here that whenever the crash probability is high, let's say close to like 10%, you can see, but it's up to you to define what is high. But roughly when it is high, investors have the shortest horizon, investment horizon, which that's what you see in panel B. Whenever the crash probability is low, for example, look at, for example, this area, right? Or look at these areas. These are these areas. That's when the crash probability, that's when the investment horizon is the highest. Okay. So when the forecast horizon is 4 months, the shortest investment horizon, it appears to be 5 months, which is below here. 5 months is like, you can see less than close to 100 days. Yeah, over there, or a little bit higher than 100 days. Okay. So in stress time, the investor's horizon is about 5 months. In normal times, the investor's horizon is about two years. Okay. So now, let's try to investigate the performance of our crash probability measure. So I will try to be slow here so that you understand exactly what is in the table. So in this table, we don't have crash probabilities. What we compute is that we have the threshold, which is 10% crash and 20% crash. Look at the top of the table. And then in the first column, we have the benchmark. We have the log. We have also the other approaches like Chabi and Laudis. On top of it, we have Chabi and Laudis. We have also our crash probability, crash probability over there. So the numbers here are not crash probabilities. The numbers here are loss functions, right? We computed the loss function as the negative of the log likelihood functions. And then we check if the difference between the loss function in Chabi and Laudis and the loss function in our framework is positive and significant. So whenever you see a positive number and significant number here, for example, it means that, for example, here it means that if you focus on one week forecast horizon, it means that the Chabi and Laudis actually lead to a significant lower losses than our framework lead to a significant lower losses than Chabi and Laudis, than Ian Martin, and in this case, than Chabi and Laudis. If you go to 1 month, there's no difference. If you go to 1 quarter, you can see that our framework lead to a lower losses than Ian Martin's framework. It leads to lower losses comparing this to Chabi and Laudis. Same for other horizons as well. Now, if you focus on 20% crash probability, you get similar results starting from 1 month's forecast horizon. You can see 658 is highly statistically significant up the way to 1 year. Okay, so this clearly shows that our crash probability measure leads to significant lower losses than the benchmark probability for most horizons. And also, if you change the threshold 10% to 20%, you get similar result. Now, all the results that I presented so far are actually obtained by using lower bounds on the preference parameters, a lower bound of 1 on the risk aversion, lower bound on 2 on the other preference parameter, which is the skewness preference parameter. So what we did next here is that we tried to estimate these preference parameters from the data using a 2-stage nonlinear least square approach. As you could see here, the first equation here on the left-hand side, you have the excess return. On the right-hand side, you have, this is our measure of equity risk premium. That depends on the preference parameter. And also it depends also on the risk neutral moment, right? That I presented this equation before. And the second equation here is more like about the variance. And this term here is also a function of the risk neutral moment. It depends also on the preference parameters. So we use the 2-stage nonlinear least square approach. We assume that the preference parameters are linear function of the market, past market returns. So we are able to estimate the risk tolerance and the skewness preference parameter, as you can see. And in panel A, we can clearly see that the skewness tolerance actually, it varies over time a lot. And as I said, not the skewness, the risk tolerance parameter varies over time a lot. And it decreases during, you can see that here, it decreases during market crisis, during the crisis period. Here it goes down. When you see these values, these are during stress times, right? So the risk tolerance is very low during stress times. It means that the risk aversion is very high, right? Now, what is also important is that during quiet times, you can see that the risk tolerance is getting closer to 0.8 or maybe 0.8, I would say here, right? Which means that during quiet time, the risk aversion is not too high. And what is also interesting in this graph, when you look at here, you have 3 graphs, 3 lines, 3 time series. You have the yellow one, you have the red, and you have the blue. The yellow is the one that you get when you use the Chabi and Laudis. The red and the blue are the one that you get when you use our approach, but the red actually corresponds to a 2 months investment horizon, and the yellow corresponds to a 4-month investment horizon, although we are focusing on 1 month forecast horizon, right? So what you see is that the red time series is actually below the yellow. So this is clearly showing that the risk aversion that you get with the red one will be higher than the risk aversion that you get with the yellow. So this actually clearly shows that when the investment horizon actually increases, the risk aversion goes down. And this is kind of consistent with a decreasing risk aversion that is, it's shown in the literature. Now, when you focus on the skewness preference parameter here in panel B, you can see that we see a large time series variation, for short horizon. When I say short horizon, this is the blue, right? And a small variation when you look at, longer horizons. By longer horizons, I mean 2 months and 4 months. The blue one is basically, this is a static period. The investment horizon actually is identical to the forecast horizon. The other two graphs, the yellow and the reds, are when you have the investment horizon of 1 month or the investment horizon of 2 months and 4 months, but the forecast horizon is 1 month. So what is also important here is that when you look at the skewness preference parameter, you can see that it's decreasing when the investment horizon goes from from almost 0 to 4 months, right? Let's say investment horizon actually coincide with the forecast horizon, that's the blue. When you increase the investment horizon from 1 month to 4 months, then you see that it goes down, right? It becomes a yellow. You switch from the blue to the yellow one. So this is also consistent with decreasing preference parameters, right? Estimate. Now, we also did other robustness check. What we did is that we use a telescopic approach. Starting from 2006, we use the past 10 years of data to estimate the preference parameters. And then we use that to check, to compare our approach to the benchmarks, the benchmark approaches. And we found that there's no significant difference. But what we noticed when we estimated the risk tolerance and the skewness preference parameter is that from 2006 to 2009, these parameters are quite unstable. And then from 2010 to almost 2023, they are stable. Okay. Now we also removed the crisis period and actually focused on the 2009 to 2023 time period almost. And over there, the risk aversion is almost close to 1, which means that the risk tolerance is close to 0.9. The skewness preference is close to 2, which is what we have used before in the previous result that I showed initially. And so we did also explore the implication of the third order Taylor expansion series in the paper. Okay, so I'm not presenting the result here, but we did explore this as well. Now, to conclude, so in this paper, we derived new expressions for the equity risk premium and the probability of crash. And we show that these physical quantity depend on risk neutral moment and also on intertemporal hedging. And intertemporal hedging is really important in this framework because it allows us to show that intertemporal hedging contribution is very important when you think about measuring the expected excess return during both times, normal and bad times, but it's more important during normal times. And intertemporal hedging is important when you measure the crash probabilities during normal times. We also show that investors, this is kind of new. We believe that this is new, that using option prices, we show that investors actually, they shift their investment horizons. They become like short-term investors during crisis period and long-term investors during normal period. And our results are pretty robust to different, when comparing these results to benchmarks of Chabi and Loudis or Ian Martins. And we also explore different specifications of different ways of estimating the risk aversion. And we found that our results are still hold. We explore like the third order implication for the third order Taylor expansion series. But theoretically, the third order Taylor expansion series should give you like something better. But we know in the literature that always, if you expand it further using Taylor expansion theory, it doesn't mean that empirically you might get good results. So there are some challenges over there because of the nature of the issue, because you need to estimate very high order moments. And the minute you get into that, messy things will happen. So then you need more options available, and liquidity and things like that. So, and for now, we are using of course, we presented the second order, the result for the second order Taylor expansion series. We present some result for the third order expansion series. Thank you very much. So I believe that I am on time.
Yes, you are. Thank you very much.
Yeah.
Well, there weren't any questions during the talk. It's actually common that there are not many questions for theoretical papers, so that doesn't surprise me. But now is your chance to ask Fousseni any questions that you would like to ask. We have a few minutes left for questions if there are any.
So let me mention that Elise is here, right? If you have difficult questions, then Elise will answer these questions. Okay.
So she's the smart person, huh?
Yeah.
I mean,
yeah.
On the empirical results, there was this big difference between 12 months and 18 months, right? So I wonder whether this is just because S&P options, so they used to be only 1 year, but at some point they became like 1 year and 2 year. So is it just due to the period, or is it a different explanation? I mean, it was like for 12 months, there was this table where it was just like all of those like different numbers in the very beginning. And for, And there seems to be like, there is a big difference between 12 and 18.
Yes.
So I wonder what drives it. Is it just the availability of 2 year S&P options? So
to get the result for 12 months horizon, so we use for example, if you focus, let me focus first on 3 months, right? Forecast horizon of 3 months. So we need to use a 3 months option. We need to also use a 12 months option, right, to get this result. Now, when you go to 18 months, you need to use not only the 3 months on the 18 months. So I think what you're asking is, you have more, option prices are more liquid at short maturities compared to long maturities, like 12 months compared to 18 months. I think your question, if I understand, is maybe, is this boost in the out of sample R squared related to the liquidity of options available for 18 months? That's your question?
Oh, yeah, I just didn't focus on the columns. I focused on the rows, and 18 kind of rows stand out because it's like goes from 6.2 to 2, 5.7 to 2. Ian Martin measure goes to negative. So seems to be a big change from row 12 to row 18.
From row, you see row 12 to row 18, which is here 5.12. I will let Elise answer this question. So, but
I'm going to try and hi everyone. I'm going to try and answer this question. I'm not sure it's specific to the liquidity of options and the differences between 12 and 18 months options. But so what we observe is that there's basically an increase of the out of sample R square up to a certain maturity. So the shorter the forecast horizon, the shorter the optimal maturity. And then the decrease in the out of sample R square is very sharp. The reason why we don't see it when we increase the forecast horizon. So if you go to forecast horizons of 4 months and more, actually you get that the out of sample R squares are just increasing and then they never decrease. The reason for this is that we just don't observe options with maturity more than 2 years, right? So we believe that if we did observe options with longer maturities, we'd probably have the same phenomenon. But for short forecast horizons, we have really like a sort of a steady increase, and then all of a sudden, like the out of sample R square becomes pretty bad. The reason for this is that for short forecast horizons, there's much more volatility in the data. If you take options with very long maturities, everything is very smooth. So in the end, it just don't bring much to the out of sample R square. I don't think the difference is really between the gap is really between 12 and 18 months. I think it's just that we'd have the same thing if we had options with longer maturities. And also, maybe I should add the reason why I don't think there's really a gap between 12 and 18 months is that we pre-process the data, so we use the volatility surfaces, so everything is kind of smooth, and we check that there's nothing really strange in the maturity dimension and in the moneyness dimension in the volatility surface. So the moments don't look, we checked moments up to order 5, if I remember well, and they look reasonable for all maturities.
Yeah, so just to add to what Elise just said, like, if in a perfect world, right, if you have options with even longer maturities, like even to 5 years, 7 or 10 years, which is, we don't have it, right? So we have a theory for that, but empirically we are limited to 24 months. Even when we say here that, okay, sometimes we need like the investment horizon actually is 2 years. It means that it doesn't mean that it is exactly 2 years, because if options were available, with options with maturities like higher than 2 years were available, then it is possible to have an optimal investment horizon that is higher than 2 years, right? So sometimes you have the outer sample R squared actually increases to a certain horizon and then goes down. Sometimes it just increases, right? And you just need option with more like higher maturities that are not even available, right? To be able to pin down the optimal. But at least this is a good starting point, because it allows us to get to boost the outer sample R squared, to know that, well, for some forecast horizons, we know how to get the optimal ones. For others, the optimal will be just 2 years, optimal investment horizon, right? So that's. Any other questions?
Okay. Hi, Fousseni, this is Lai.
Oh yeah, hi, how are you?
Hi. So I have a question on this one. Since you're showing this out of sample R square, what is the sample split you have? The in sample is 90 days, did you say, or 10? I didn't quite get what is the in sample size and what is the out sample size of the data set? How do you split it?
So here, what we did is that, so, okay, when I talk about 90 days, it's not in this setup, okay?
Okay.
So in this setup, what we need, first, we need to, as long as we have the preference parameters that are fixed here, right? They correspond to lower bounds on the preference parameters. What you get is we have a measure of our equity risk premium. Then the next thing that we did is just using the auto sample, provided by Gourier language, right, to compute the auto sample R squared. So here there's no, I would say, no overlapping or no bias, nothing. So it's just that we specify the preference parameters. But later on, when I mentioned that we kind of optimize the investment horizon over using the past 90 days, like using a 90 days windows, I think that could be related to your question. But this table is kind of, I don't know if your question is related to this table or is related to more specifically to what I said later.
Hey, so you're out of sample R square, you can plot a time series of that, right?
A time series of
is a rolling
sample
window you're doing, or is it expanding window? No.
Here, the auto sample R squared, I kind of, at least we don't have a rolling window for this one, right?
Not this one.
No, for this one, it's really the out of sample R square over the whole time. So there's no training here.
Yeah, there's
no
no training.
and out of sample,
Yeah.
right? The only training we need is in order to estimate the preference parameters. But in this table, they're just set to 1 and 2. So there's nothing
Yeah.
to train. You just take the options at time t, you plug in the preference parameters, and you get an estimate for the equity risk premium. So then we basically compare this estimate to the realized returns over the entire sample. So there's no rolling window here. It's just the it's not out of sample, actually, it's a whole sample
yeah.
R square. So it's out of sample by design, but there's no in sample